Welcome. Welcome to the Learning Glass studio for another Learning Glass video. So, today we will talk about a big part of engineering, units and dimensional analysis. So, to do engineering calculations, you have to make sure you're in the right units. And it takes a lot of practice. And especially if you're working in America, because here in America, we use different unit systems, and it's not as easy as the international system of units, SI unit, System International. So starting with force, using Newton's third law, force equals mass times acceleration. The SI units are pretty straightforward, that force is the official SI unit of force is newtons. So this would give you 1 Newton equals 1 kg, which is the unit of mass, times 1 meter per second squared. So the Newton, it's 1 kilogram, 1 meter accelerated a second squared. So it's meters per second. That's where the Newton comes from. But it's different if you're in America. You would have to use pound force. So we use pounds, but whenever we use pounds, 99% of the time, we're saying this is pounds, the force applied by weight would be the direct analog. 100 pounds means you have 100 pounds of force in Earth's gravitational field. And what corresponds with that is the mass that goes along with that is kind of weird. It's the slug. And 1 slug per 1 foot per second squared. That's how pound force is kind of defined. It's kind of a retrofit, actually, because the slug itself, it's not used that often. It's more to describe mass. It's basically tied back to force. And so, for example, for weight, which is a force, weight just refers to the force of the mass in the gravitation, whatever the mass under the gravitational field, it's mass times the acceleration of gravity, where in America, G on Earth in America is 32.17 feet per second squared. So the acceleration due to gravity in SI units is 9.8 meters per second squared, but in America, it's 32.17. And tying with that is that if you were to apply this to the weight here, there's another kind of confusing point in America, is that 1 pound force in America can also, but there's another kind of subtle concept where if you were to be exposed to the Earth's gravitational field, then in Earth's gravitational field, 1 pound of force in gravity corresponds to 1 pound mass. So this is the Newton's law here. If you were using SI units of G for the weight on Earth, 1 pound force corresponds to 1 pound's mass. If you were just standardizing by 1 foot per second squared, 1 pound force corresponds to 1 slug of mass. So in America, extending this example further, in America, if I say that I weigh 100 pounds, verbally, what I'm saying is that this is 100 pounds of force. That's what I mean by that. And if I were to put this in some type of, to see how many slugs, some unknown amount of slugs in Earth's gravitational field, feet per second squared, what that would be is that 1 pound force, or 100 pounds on Earth, corresponds to 3.1 slugs on Earth. And this weight would the mass would not change depending on where you are in the universe. 3.1 slugs is the same mass. But depending on your gravitational force field, you might give a different weight depending on where you were in the universe. And so 3.1 slugs on Earth would give 100 pounds of weight. And comparing that to pound mass, so this 100 pounds force on Earth corresponds to 100 pounds mass on Earth. And so those are assuming you have Earth's gravitational field. But so because of these two definitions here, pound mass is describing mass, slugs is describing mass. So these are two same dimensions. So putting those all together, 1 pound mass equals 32 slugs, or this gravitational. So in engineering, if you're doing engineering calculations in America, these are the types of things you may come across in terms of force and things like that. Pounds per square inch also come into play. So yeah, let's talk about pressure then. Pressure, by definition, is force exerted per area of on a surface, normal to the surface. And what comes out of the SI units is the force of newtons per meter squared. That is the two SI units, newtons and meters. And newtons per meter squared is the SI units for pressure, and that has been given the name of pascals. SI, it's pascals. Some dude named Pascals got the name. So that symbol for that is PA, pascals, equals 1 pascal equals 1 Newton per meter squared. And as we know, in America, the unit for force is pound force, which is, that makes sense. We would use pounds for force. And then instead of using pounds per feet squared, pounds per feet squared, we use pounds per inch squared. So pascals, 1 Newton per meter squared. In America, it's pounds, which means pounds force, per square inch. Pounds per square inch, PSI, equals 1 PSI equals 1 pound force over inches squared, which it's not as cohesive with the per feet squared. Then that raises the question, what is an inch? What is a meter? Well, in America, we're kind of familiar with this. 12 inches per 1 foot. And 1 foot's about yay big. So 12 inches, 1 inch is about yay big. And then the standard for most of the rest of the world is a meter. So that's about 0.3 meters. So 1 yard is 3 feet. 1 yard is similar to 1 meter. It's not the same, but it's similar scale of length. Okay, this is the length scales between American units and the SI units. And oftentimes when we measure and quantify pressure, we don't have to, but it's very convenient to use reference pressures. And the most common reference pressure is Earth. Depending on where you are on Earth, the atmosphere, like this room, the outside, there's a pressure of the surroundings, the gases in our atmosphere, and literally 1 atmosphere is a decent average to describe typical outside surroundings. And this depends on where you are on Earth, of course. And the reference is close to sea level, which is how all across the globe, the water spreads out across gravity across the whole world. And if you're at the level where the sea is, that's a good reference point. That's close to what 1 atmosphere is in pressure. And in terms of pounds per square inch, if you are 1 atmosphere, then you're exerting 14.7 pounds per square inch, and that's absolute pressure. And you're not using a manometer or some dial that's 0 at the surroundings. It's saying that, if you were to go from perfect vacuum of 0 pressure and then build up, 14.7 would be an average reference of the Earth. And in terms of SI units, this will be 101 kilopascals. 101 kilopascals. And so 1 atmosphere is a nice average, but that's not as clean and round. So another SI unit, which is more clean, would be, I'll put it right here, 1 bar equals 100 kPa. Or in terms of just PA, it's 10 to the 5 PA. 1 bar. That's a nice reference because it's cleaner. You know that it's a 10 to the squared kPa or 10 to the 5 PA, which is 10 to the 5 Newton per meter squared. So 1 atmosphere and 1 bar are pretty close. They just have this little 1% or so difference in the absolute value. So this would be an absolute gauge. As opposed to gauge pressure. So reference pressure, if we were to convert units, so notice P, we're talking about gauge pressure, is the absolute pressure of your system you're trying to measure minus some reference pressure. And oftentimes the best reference pressure is atmospheric pressure, some ambient pressure of the surroundings. And if you were to measure delta P, some pressure drop, delta P equals P absolute, or no, you're just saying you have some pressure drop, P1, P2 minus P1, for example. You can say this is P2 absolute minus P ref minus P1A absolute minus P ref, where the reference cancels out because it's the same reference. So in this example, if you're taking the difference between 2 pressures, it doesn't matter if you're talking in terms of gauge or in terms of absolute, it cancels out. So if you're consistently using gauge or consistently using absolute, the reference cancels out. However, for engineering calculations, you should you should remember to be careful and convert to absolute. Convert to absolute, because if you're taking the ratio of these two, P2 over P1, that's where you can run into problems. So P gauge does not equal the absolute ratio. So when you're using the ideal gas law or taking the ratio of pressures, the gauge pressure will mess you up. You should convert to absolute. That's the real answer there. This is wrong, this is right. And they're not, you're gonna get different answers. If you're taking the difference, then that reference pressure will cancel out. And so just a quick example of converting units, the idea is to multiply the units you are in by a ratio that equals 1. Multiply it by 1, but that ratio converts. So 20 pounds per square inch absolute. Make sure you're in absolute, because you'll get the wrong answer if you're not. The relation, if I wanted to convert that to kilopascals, for example, like let's go to kilopascals, you would take that 20 psi absolute, and then you'll multiply this, your starting units, by a ratio that equals 1 that cancels out this unit. It'll be, you'll have to find a relationship of 1-to-1 of psi to kPa. So here we are here. 14.7 psi per 101 kPa. This is like a nice reference, and it's both the reference pressure, a common reference pressure, common atmospheric pressure, and it tells you how each of these units are related to each other. So if you had 14.7 psi absolute, these two units would cancel out in this multiplication, and the ratio would be 101 kPa. So in terms of the units, if you had 14.7 psi absolute, that would give you 101 kPa of absolute pressure in SI units. And by this is 1-to-1 ratio here in terms of value of the actual pressure. But by using this ratio, you would cancel out, putting PSI on the bottom, it'll cancel out this, giving you this new units of, let's see, what does that come out to? 138 kPa. So that's one example of converting units. And as we may have experience with, this is part of engineering analysis, is getting your units straight, and throughout your calculations, making sure you have consistent units and are properly converting from one to the other. So continuing with gauge pressure, let's put this here. Gauge pressure is useful, in some engineering applications or some systems. All gauge pressure is all that is needed, and it's very easy to read that off of a dial, off of a gauge, pressure gauge. Pretty much all pressure gauges are given an output depending on gauge pressure of what their surroundings are. So, in terms of the gauge pressure, units wise, common units in America for gauge pressure is inches of mercury. And there's about 30, well, before I go there, when you hear inches of mercury, you should think America, and this is vacuum. Talking about vacuum systems. What does that mean? It means negative gauge pressure. It's below the ambient pressure. Negative gauge, negative gauge pressure. That's a common way to describe the pressure under negative gauge is inches of mercury. So if you hear pressure in inches of mercury, it's probably talking about a vacuum system, and it probably would be a positive number, so like 10 inches of mercury, and what that really means is that 0 is ambient and you're 10 below ambient. So it's negative 10 gauge pressure, really. But oftentimes you hear this without the negative sign. And for some perspective, if you were in these negative scales, it would be like negative 30 inches of mercury is about negative 14.7 psi. So it's about double. The units of psi is a negative gauge. It breaks down into about double for inches of mercury. But in another one is in the SI units, which I like better because it's always going to be absolute. It's called millitorr for vacuum. Continuing with vacuum, a common unit for that, it's millitorr, where 760, so this is absolute, and there's about 760 torr per 14.7 psi. And that comes from millimeters of mercury, actually. 1 torr is 1 millimeter of mercury. And in SI units, when you're talking about vacuum systems, we often use millitorr absolute, so it's trying to stay like millimeters of mercury rather than inches of mercury. And they're trying to be smaller, even smaller than 1 torr. So 760 torrs to get from 0 to 1 atmosphere. And then vacuum systems, they operate on the millitorr scale, which is trying to get like 1,000th of 1 torr level of pressure. Okay, pressure is part of the ideal gas law. So ideal gas law, P, there's many ways to write it, of course. Let's talk about the mass version. PV equals MRT. Brings a whole world of dimensional analysis with it. Or you can say pressure is rho RT, converting volume and mass to density, where R is a gas constant. It's not the universal gas constant, it's a gas constant which changes depending on which mass of the gas you're talking about, which molecule of gas you're talking about. And the universal gas constant is only the number of molecules you're talking about. It doesn't depend what they are, it just depends how many there are. That's why it's universal. This, when you're talking about mass here, it depends on what you're talking about. So for air, if you're talking about an air system of gas, then R is about 0.3 in terms of units, kilojoules per kilogram Kelvin. How does energy come into play? Well, that's the basis of the ideal gas law. It came from the idea that temperature is a proportional parameter value that increases with increasing kinetic energy, decreases with decreasing kinetic energy of the gas. And the way that this energy equilibrates across a volume is that, so this is a unit of energy on this side, this is a unit of energy on this side, PV will give you energy. And so the higher the temperature, the higher the kinetic energy, and the larger the volume, the lower the collision rate. The higher the volume, the lower the collision rate. The higher the pressure, the higher the collision rate. So these two counteract. They both determine the collision rate. That's why these two affect the collision rates, which affects how this temperature and energy equilibrates. So how does the units work out? Is, well, let's look at the units of R. R itself, if we were to solve here for R, it will be PV over RT, where if we're using SI units, that would be newtons, or let's go with pascals. Pascals times volume, which is meter cubed, and then divide by R, which I just gave you one example, could be in terms of, let's call it joules per kilogram Kelvin, and then Kelvin there on the denominator as well. So that's what the units we're multiplying in this equation would be for R. Okay, how does that give us R? Well, pascals is a nice clean newtons per meter squared per Pascal. Should do this. So 1 Pascal is 1 newtons per meter squared. Should be the other way around. So we want to cancel out 1 Pascal. So 1 Pascal is equal to 1 Newton per meter squared. So let's put Newton here and meter squared here. So this is the Newton per meter squared here per Pascal. This is a ratio of 1 here. And yeah, so this would cancel out Pascals here. Now we're into newtons and meters squared. So we'll elaborate more on this, but spoiler alert here, energy, the unit is joule. J, where 1 joule equals 1 Newton meter. We'll elaborate a little bit on that, but that's how we'll go from pascals to newtons per meter squared, then to Newton times meter, which would give us energy. So 1 joule is, you do it the other way. 1 Newton meter is equal to 1 joule. So here we have meter squared, so this meters cubed cancels out. There's no more meters left. Here, Newton cancels out, Newton. Kelvin here cancels out here. Joules per kilogram. Wait, what am I doing here? PV, R is joules per kilogram Kelvin. Oh wait, that's what I did. I am tripping. This should be, sorry everyone, this should be joules per MT. M should be here instead of this. Sorry everyone, I am tripping here. There should be 1 over kilogram here. Did I mess everything up yet? Maybe not. So Kelvin should not have canceled out. Yeah, so this is PV VMT. So we did need this joule over here so that we can cancel out pascals to Newton per meter squared, then Newton meters. So now we have joules. Kelvin stays there. Kelvin stays there and kilogram stays there. So yeah, that checks out now. All of these cancels out except for these three. 1, 2, 3. So that's an example of how PV is energy. Newtons per meter squared times meters cubed equals newtons per meter. So PV you can describe in terms of joules as well. Here on the left side of both sides, but PV itself is a unit of energy. Okay, so yeah, that's good. Okay, another application to energy would be mechanical work. So, energy is energy. It's very useful, and depending on the system and the thing you're focusing on, there can be a lot of different ways to think about it and even quantify it in terms of units. So mechanical work is a whole useful world, and depending on whether you're in America or not, there's different ways to describe it. So the best way to start for mechanical work is the definition of mechanical work is W, mechanical work, by definition, is the integral of some force over some distance. So that pops out units right away, especially if you're in SI units, nice and clean units for the most part. This would be newtons per meter, as I just said, would be joules. So that makes sense. But things get a little more dicey if you're in America. And that's where the whole world depends on the context of what you're trying to do in the engineering calculation in America. So, in engineering, there's a lot of different analyses you can do. We can break that down into a mechanical application, which would be force and forces and weights and things like that. And then a lot of the stuff is electrified, so you have to talk about what the electricity you get tying into the mechanical work. There's a lot of applications in that. And then another world related, but can be separate in some cases, is thermal world. So whether you're trying to heat something up for a process or you're trying to have HVAC applications of heating or cooling a space or heating and cooling a process, that is an interplay of energy as well. And in SI, System International units are more consistent, but once you get into America, it's much more annoying because we have a lot of different old systems that are still into play that do not cleanly coincide with each other. It takes a lot of practice to navigate both the concepts and the units themselves. Because there's a lot of old reasons of why these units exist, and at one point it was like all easier, it was just more straightforward because that was the system we had, but trying to make one unified system of the System International shows how the older systems are more confusing. Okay, so in terms of going back to mechanical, if we were the SI units of mechanical, that would be, I'll put this back up here, mechanical energy, starting from mechanical work. You have Newton meter, joules, or work would be kilowatts equals 1 kilojoules per second. Okay, those are nice and useful. Joules of energy or power, kilowatts, kilojoules per second. But in America, things get a little dicey. You would have, okay, if energy started continuing with this F delta X in America, that would give you foot-pound force. So pounds of force is the force, and then foot is the length. So literally 1 unit of energy in America is foot-pound force, which is weird. And it's not too common, but it is pulling from this system. One foot-pound force equals 1.36 joules. Say 1.4 joules. So that's a unit of energy in America. And then power would be horsepower. Horsepower, 1 horsepower equals 0.7475 kilowatts. So that's for mechanical energy. Energy of mechanical work, mechanical energy, one way to describe it in America would be foot-pound force. We talked about the mechanical side of these energy units, and to get a feel for the thermal side, it's nice to look at how this one major applications of the thermal side we can look at in terms of HVAC, heating, ventilation, air conditioning. And heating, ventilation, air conditioning is very useful for space. Space cooling, meaning not outer space, but a room. Heating and cooling of rooms for personal comfort. That's super important. But the same technique of HVAC is also a very useful approach for processes, for manufacturing and controlling different things. Controlling power, electrical power grid stuff and things like that, controlling manufacturing plants. Air conditioning or heating loops can be used to control the temperatures up and down. And the standard that we still rely upon is the vapor compression cycle, which is one type of reverse heat engine for heating and cooling. And a simple diagram of a refrigeration cycle in terms of how it works as a reverse heat engine is the simplest design or the simplest schematic would be you're operating between a cold reservoir or some cold temperature and a high temperature. And in a refrigeration cycle, what you're trying to do is you're trying to have some heat transfer at cold temperature so that you either have some space, a refrigerator, or some process that you're trying to keep at a low temperature. How do you do that? You transfer energy from cold, let's say this is colder. So you're trying to keep this cold. How do you do that? It's by having a cycle where at some stage this refrigerant is colder than this space. By doing this, the energy it stays cold because the energy is constantly going from cold to colder in the refrigeration cycle maintains. But we're still reliant upon a mechanical device where this is a compressor in the compression cycle, the vapor compression cycle, where you have to put some mechanical work in. There's a drive, a mechanical pump or compressor. Then what we haven't been able to avoid is, even though we're getting this energy to keep this cold, we're putting mechanical work in to keep this cold, we cannot avoid some high temperature dissipation of energy to the surroundings. So this is what we're designing this space for, to cool this. And by the second law, we cannot have this without a high temperature source. And a big part of this too is there's a big pressure drop, and this gets sprayed through a nozzle. And once you have a high pressure refrigerant and you spray this refrigerant into a low pressure, it gets really cold. That's how it works. The mechanical work brings it to high pressure. Then you expand this through some nozzle to give a big pressure drop from high to low pressure. Once you do that expansion, it gets really cold. The refrigerant gets cold when you do that, and that allows you to go from cold to colder. So we have some energies here. As we know, to get a refrigerator working, to get our air conditioner working, most of the time we plug it into some electricity. That's where this comes into play. So there's mechanical work of electricity coming in to power the mechanical work of this compressor motor, but there's also energies involved where there's heat transfer at high temperatures out, and there's heat transfer at low temperatures into the refrigeration system, out of some space, my seltzer, the room, or some industrial process of keeping things cool. And so there's already three types of energy here. Mechanical work in, cold temperature heat into the refrigerant, high temperature heat transfer out of the refrigerant. And in America, depending on which one of these are talking about, you'll use different units. So in America, there's tons of cooling. So when you ask, when it's a HVAC system, an air conditioning system you're trying to design, or a chiller system to chill an industrial process, the capacity of that chiller or the capacity of that air conditioner in America, they use this thing called tons of cooling, which comes from tons of ice. The old calculation that used to be done was, you're saying this can make this much tons of ice, which can be used, it's like an ice house. You centralize this refrigeration cycle to make ice, then you can take that ice elsewhere. That's how it used to be done. That's where these old calculations are from. But we still use this tons of cooling to describe the capacity of this Q cold here. So Q cold, that would be the tons of cooling, and where 1 ton equals 3.5 kilowatts of cooling. So again, SI is nice because kilowatt is a kilowatt, energy is energy. I guess the American system is more specific, but it can be confusing if you didn't get all the practice. But if you're talking about heating, like if you're to try to burn fuel to get a heating furnace or a boiler, you would quantify a boiler or heating or a furnace, and you're burning fires, there's BTUs coming in. The energy coming in from the fire, it's called BTU, British thermal units. So this would be heating, where 1 British thermal unit equals some amount of energy. This is some amount of joules. I didn't write it down, but this is joules. Some amount of joules. Look, I'll give you guys for homework. It's not a rate, it's joules. And in terms of this, either using this in a boiler or using a fire for a room. So heating a room using some BTUs, one guideline would be that you need 10,000 BTUs per per hour for a 400-foot squared room. If your room was 400 square feet, you would need a furnace or some type of heater that can transfer 10,000 BTUs per hour. That's how that would work. Then, in SI, the SI units would be, for this, would be kilowatts heating or cooling. And then the motor part, so HVAC, it's kilowatts heating or cooling, and then the motor part is different. So SI would be the drive. So the motor part, let's call it the drive motor, or the mechanical part would be SI units, would be kilowatts, of course, kilowatts of the drive. In America, this would be horsepower. So I guess it's more specific. In America, you would say this is an HVAC with a 10 horsepower compressor motor. Because when you're talking about horsepower, you know you're talking about the motor, that's good. But it doesn't tell you about the capacity of its cooling. That, if you're talking about the capacity of cooling in America, they would use the units of ton. So these both are units of energy, or power is horsepower, tons is capacity. And they're both kilowatts, but they're telling you one is specifically for the mechanical part and one is for the heating or cooling part. I guess it's nice in the SI units, it's all kilowatts, units of kilowatts, but you would have to specify whether you're talking about kilowatts of the compressor motor, that's where the electricity goes into this device. And then once you get this running, depending on the refrigerant and the flow rate and stuff like that, you would get a different amount of heat transfer coming in of cooling or heating capacity. And a heat pump, it's the same design, it's just optimized for a heat pump. You would want to design around this. So a heat pump takes in electricity, uses a refrigeration cycle, and you do have this cold part as well, but you're designing to get this high temperature to heat up your room or something like that. That's what a heat pump's for. Okay? So one note about this is that the coefficient of performance is how you would quantify this. COP is by definition the cooling rate you're trying to achieve over the drive power, the mechanical energy you would have to use. And this is actually, note, this is tons over HP, so you would have to convert this to kilowatts. You would have to convert the units to make sure you're consistently comparing the two together. Okay. So stuff like that. Yeah, there's a lot of different units and different discussions. So yeah, with that, there's a lot of different things that can come up. And in thermal fluids, a lot of it comes down to energy, and it takes a lot of practice to see how these are all related together. And especially if you're in America, you have to keep track of these older unit systems that don't always easily convert into one another. Okay, so couple quick examples for food. there's a unit of calories. That's what we call in America 1 big calorie. When you see a food label, that's actually 1,000 calories. And a calorie is actually the energy for water to have a change of 1 temperature, of 1 degree Celsius. So that's what a calorie is. If you had water, it'll take 1 calorie to go 1 degree Celsius. So that kind of makes sense. That's nice. But it's a unit of energy, so 1 small calorie is 4.184 joules, which might sound familiar because the heat, this like ties into heat capacity. The heat capacity of water is 1 calorie per degree Celsius. Or in terms of joules, the heat capacity of water is 4.18 joules per Kelvin. Gas volume flow rate, we'll use the ideal gas law. If you have a gas, you can describe the flow rate of the volume by the mass flow rate, RT. And so the volume flow rate depends on the mass flow rate, the gas constant, and the temperature and pressure. So that's why it's important that when you're talking about gas flow rate and you're trying to describe this specific gas flow rate, you should also specify the temperature and the pressure. That's why you often see standard in front of this S. STP, there's different standards. I use 300 Kelvin, 1 atmosphere. So that would be 300 Kelvin, 1 atmosphere here. And that's why you see a nice thing about SI, you have this 1,000 centimeter, should be 1,000 centimeter cubed equals 1,000 milliliters, 1 liter, and then in terms of gallons, that equals this is America, 26 gallons, which is 0.035 cubic feet. And for flow rates, V, you can say this is SLPM, standard liters per minute, meaning you're specifying this. Or in America, USA, it'll be standard cubic feet per minute. Okay, so those are some notes I had. A lot of this stuff comes up, especially if you're in the America units. There's a lot of these little things that come up in terms of feet versus inches, and so forth. So with that, I'll see you guys next time. Thank you very much.